Sébastien Tanguy to you. Sébastien did his PhD with Alain Berlemont at Korea and Rouen. At the time, we were both very excited. We were all very excited about atomization. And so he developed the famous RTR code of Rouen, which was one of the really first very good volume of fluid combined level set volume of fluid codes to do atomization. I don't know whether you are co-author of the Perry-Match paper at that time.
Yeah.
Then he moved to Toulouse, where he continued developing level set methods and others on phase change, and that's what he's going to talk to us today.
Thank you, Stefan, for this kind of introduction. So this talk is about the numerical simulation of nucleate boiling, and we are going to be interested in nanoscale models in the microregion, which appears in the vicinity of the contact line, to integrated models for large-scale system to predict bubbles at maybe industrial scales for future application. This work has been carried out at IMFT with several collaborators, as Ana Federica Urbano, Lorik Torres, Leo Tranier, and Catherine Collin. So we are just the first step on nucleate boiling. We distinguish two main regimes, the contact line regime and the micro-layer regime. The contact line regime occurs at moderate Jacob number, so moderate superheat, wall superheat. And this is just a classical bubble growth with a bubble shape which is similar to the which reproduce the mechanical equilibrium, static mechanical equilibrium shape of a bubble. And in this contact line regime, we can have also what is named a microregion, which size is very low, approximately 100 to 200 nanometers. And we can observe, we can deduce this, the existence of this microregion by measuring the contact angle, which locally varies, which can temporally varies with the wall superheat. And this apparent contact angle is a kind of signature of the microregion. Here you have the contact angle in the microregion at very low scales, and this one is the apparent contact angle that that experimental guys are measuring at lower scale. So there is a transition between this microscopic contact angle and larger apparent contact angle, and in this region, high heat flux can occur and have an impact on the bubble growth. Another regime which appears for higher Jacob number, that means for higher wall superheat, is the micro-layer regime. So the wall superheat is so high that the contact line cannot advance at the same velocity that the interface, and this leads to the formation of a long liquid film. Here we have some signature of a micro-layer with a strong heat flux due to the quick, very fast advance of the interface, and which form a long liquid film between the bottom of the bubble on the superheated wall. The micro-layer is driven by hydrodynamics, thermal and hydrodynamics phenomena, whereas the micro-layer, whereas the microregion can be related to some nanophysics phenomena. And the thickness of the micro-layer is about 3 to 5 microns, so maybe other value can be found, but maybe between 1 and 2 microns, whereas the microregion is much lower size. Okay, so what? Oh, here we have a snapshot of a computation which has been performed in the micro-layer regime, where we can see this very long and thin liquid film, which can be captured with direct numerical simulations. Okay, just some preliminary results in the contact line regimes that we have obtained several years ago. In a simple case, in the contact line regime, we have done some axisymmetric simulation with wall thermal conduction for several Jacob number, about 20, 21, which correspond to a wall superheat of 7K, an apparent contact angle of 50, which is typical of water. And we simulate that kind of thing with Navier-Stokes equations for incompressible flow, which is coupled to energy equation on related jump condition across the interface. In this case, we do not add any models at the contact line. This is just continuum mechanics. And we have performed several comparisons with experiments. Here for the wall superheat of 7K, or here for a wall superheat of 8.5K. We show a good agreement with the experiment of Son et Dir with a relative error of about 5% on the bubble departure radius or bubble departure period. And our simulation are well resolved. This is what we can observe here with several mesh size of between 10 microns and 5 microns seems enough to have a well-resolved simulation, which is grid independent. So, if we conclude about this, it seems no extra models has to be imposed at the contact line for this case, since the result seems good. So this was just a quick introduction, and before going further, here are some numerical details, some details on the numerical method which are used. We use a level set method, which is a Eulerian interface capturing method, which is a bit similar as both, except that it does not strictly conserve the mass, but it has some interesting properties on the continuity of the function, which can be enforced by imposing a resistance equation, which ensures that the norm of the gradient of D is equal to 1. This means it's a distance function, and it is a very continuous function that helps to compute the curvature at the interface accurately and to have also good stability properties. The Gauss-Fried method is used to impose the jump condition across the interface. It consists in extending continuously discontinuous variables before discretization. For example, if you want to compute the derivative at this point, you will, if you have an interface between these 2 points with a jump here, you will build an extrapolation of this function on the other side of the interface, and next you can compute your derivative with the ghost point here, on the derivative at this point with the ghost point here, to avoid to define a fictitious interface thickness. So it has good properties for liquid vapor fast change simulation, also to reduce parasitic currents across the interface. Finally, our solver for boiling is based on the solver proposed by Gibou and co-workers in 2007. It is roughly described here. We solve separately the both domain, the liquid domain for the temperature in the liquid domain and in the vapor domain, by imposing directly boundary condition at the interface, which is simply the saturation temperature at the interface. And we have the same equation for the vapor. And next, by after computing the temperature in both phases, we can deduce a jump on the local heat flux, and it will give us the mass flow rate, the boiling mass flow rate at the interface, which is the critical parameter for the numerical simulation of liquid vapor fast change. Okay, so all the simulations that will be presented next are based on these general principles. So the 3 points in this talk will be on the numerical simulation of nucleate boiling in microgravity. And we will see in this case that a micro-region model can be mandatory. Next, I will talk quickly of numerical simulation in the micro-layer regime, so numerical simulation of the micro-layer formation. And finally, I will talk at the end on the development of integrated models for large-scale computations. So our study on microgravity are inspired by the by the Ruby experiments, which has been said in ISS by a team of several universities, in which collaborates Catherine Collin, my co-author on the paper related to this study. It is a bubble which is heated by a wall by a Joule effect in the solid. The liquid is a perfectly wetting liquid, which is very different of the previous case where we have done simulation with water. So in this case, this is a perfectly wetting liquid, FC72. And we initialize our thermal field from an analytic solution of the heat equation related to temporal heating time. We have done simulation in axisymmetry with axisymmetric configuration with mesh size between 2 and 16 microns. Here we have here just a picture of the droplet which is growing in microgravity condition. And here a sketch of the numerical simulation with the wall which is solved, the saturation temperature in this part, and the bubble who is growing in this thermal boundary. The first results we have obtained are the following in this animated movie. And we observe a very large discrepancy between our numerical simulation in blue and the Ruby experiment in red. We have checked the space convergence with more and more refined grids, and we obtain that our solution is grid independent. So this is not a truncature error that generates this discrepancy between the blue curve and the red curve. So our assumption was maybe we neglect important effects at the contact line, and maybe the microregions that we have talked before can have a significant impact on the overall bubble growth. So we tried to implement a microregion model to couple it to our DNS solver. So this is the same figure as previously shown. Some feature of this microregion model, many microregion models exist, and there's not a clear consensus on which one is the best, because there are many assumptions and which are very difficult to validate at so small scales. But all these microregion models have two main ingredients. They provide an apparent contact angle which depends on the microscopic contact angle and on the wall superheat. And also they provide an integrated heat flux along the microregion. And so for our DNS, our strategy for the coupling with DNS will be to implement this variation of the contact angle. This one is an input of the microregion model, and this one will be the input of the DNS. So we have to solve in the previous step the microregion model, and next to give it as an input for our DNS, for the apparent contact angle, and also for the local heat flux inside the microregion. Our study is based on the Mathieu's model, which has been developed in 2003. This is an extension of the well-known Stefan and Bus model, which has been published previously, but the Mathieu's model enables to incorporate a partially wetting effect. I mean that Stefan model is restricted to 0 contact angle, so perfectly wetting fluid, but perfectly wetting fluid is a very specific case, and even fluid, most of fluid have still a microscopic contact angle, even if its value is very low. So Mathieu's model is interesting because it enables to handle with low microscopic contact angle. This is Mathieu's model. It is composed of this is a set of 5 coupled equations, which is the two first are kinematic representation of the interface. This one comes from is the coupling between the contact angle variation with the local pressure jump. This one comes from Stokes' equation, for which we have given a pressure distribution which is related to this velocity distribution in that kind of configuration. This is the flow which is obtained from the analytic solution of the Stokes equation in a wedge, where with a source term of mass at this point, a sink term of mass at this point. Finally, we can define a heat flux distribution from this equation, which is a kind of energy equation, with some nanoscale ingredients as a thermal resistance at the interface, and a slip length also, which appear in air. And this thermal resistance depends on an accommodation coefficient, which is not always perfectly known for any fluids. So we have to presume of the value of this accommodation coefficient. Here we have some typical curves of the heat flux, integrated heat flux in the microregion, depending on the superheating between the wall superheat between the wall temperature and the saturation temperature at the interface, and here variation of the apparent contact angle with the wall superheat. We see that both models give very similar results on the total heat flux, and the slight discrepancy can appear on the apparent contact angle. But the question that we have to face is how to couple this microregion model with the direct numerical solver, especially from the point of view of conjugate heat transfer at the contact line. So what our model gives us heat flux, a total heat flux in the microregion in red, but we can define a kind of linear relation between this local heat flux, microregion heat flux, with the wall superheat. Of course, we do not have any analytic relation, but we have to define some coefficient to define a linear relation, depending on many data of simulation which have been performed for several superheat and several other and variation of several other variables. From the point of view of the coupling with the fluid solver and the solid solver for the temperature, for the energy conservation, what we have to impose is the continuity of the flux in the cell which is caused by the contact line. So in the cell that contains the microregion, we have to keep in mind that the microregion is much smaller than this cell. This is just a small part of this cell. And we have to impose the continuity of the heat flux, which is provided by the microregion solver, on the heat flux that will be sent from the liquid to the solid. And finally, what we observe is if we egalize both relations, we simply have a Robin boundary condition on the temperature. And the important point is the wall temperature is never known. It is a part of the solution. So initially, at the initial step of the computation, the wall in any iteration, the wall temperature is never known. It always evolves in time. So the conjugate heat transfer between the solid and the fluid domain can be imposed for this cell by imposing a Robin boundary condition when we are solving our solid linear system for the temperature. So this is the first point. But if we do not do this implicit coupling, but just trying to egalize the flux between the two systems, the interface will tend to thermalize the wall, which will tend to take the saturation temperature, and this will result in a vanishing effect of the microregion, but this is artificial. Only an implicit coupling that implicitly enforce the microregion flux when solving the heat transfer in this mesh enables to account for this microregion effect. The other point is how to distribute a strong mass flow rate in a cell which contains the contact line. In fact, this is a case where the microregion heat flux is very high in comparison to the local mass flow rate involved by boiling in other cells. And what we observe is just a red spot which is much higher than other points. And it's a result of this a lot of numerical instabilities and difficulties to impose the correct value of the contact angle at this point, because the heat flux is so discontinuous along the interface. The mass flow rate is so discontinuous along the interface. So to overcome this problem, we undertake to smooth this microregion heat flux on approximately 5 to 10 computational cells along the interface. And this is here the smoothing. The smoothing is performed with a Gaussian function, and we ensure that the total microregion heat flux that has to be imposed is maintained, is conserved. And here we have a distribution of the microregion heat flux along the interface, which is also prolongated along the normal at the interface. And here we have an addition between the microregion heat flux and the classical heat flux coming from DNS. And we have a much more continuous function, which helps to stabilize the computation. Clearly, this is an artifact, but this is the only way we can find to have a stable computation in case where the microregion heat flux is very high. And here we have a typical local velocity field in the region that contains the contact line with here the boiling mass flow rate from DNS, and to which has been added the microregion heat flux. Finally, we come back to our previous comparison between the Ruby experiment now with the microregion model, and we have now a very good agreement between our simulation. This is the same kind of simulation, but now the agreement between the DNS with microregion with experiments, Ruby experiment is very good, and we see here the difference which is involved by the microregion, and this difference is clearly very important. So this is a good point. We think that this is not a clear proof, but we think that microregion can have a strong impact in this case. But in the previous case, it has no impact. In this case, it has a strong impact. So we have a kind of many questions. But this is not the same fluid. Here we have FC72, so perfectly weighting fluid, whereas in the previous case we have done simulation with water. And the accommodation coefficient can be very different between these two fluids. Okay, before talking further about accommodation coefficient, I will talk here on the strong impact of the thermal conductivity on the microregion. We saw the coupling between the solid wall and the microregion in the previous slides. And here we have done several simulations of with microregion model and without microregion model for several microscopic contact angle and several wall thermal conductivity. And what we observe is for a small wall thermal conductivity of 1 watt per meter per Kelvin, which is roughly similar to the thermal conductivity of water, we do not have a strong impact of the microregion. On the wall jump in the temperature jump in the microregion is very moderate, less than 1 K. And the correction on the apparent contact angle is also very moderate, because here we have the microscopic contact angle and here the apparent contact angle, so the correction is very low. In the case where we consider a larger thermal conductivity for the wall, for the solid, we have a much stronger impact of the microregion, as we can see here for low microscopic contact angle and here for higher microscopic contact angle. Here we have some variation of 20% on the equilibrium diameter of the droplet, of the bubble, sorry. Finally, another interesting property is the mesh convergence with high solid heat conductivity. So if we do not use any models at the contact line, we observe that for high wall thermal conductivity, convergence is not evident. There's a kind of difficulty to convergence because the thermal field is a bit singular in this region, especially for high wall thermal conductivity. Whereas in the case we use a model, the space convergence for several mesh size is much more evident. So we had a model that integrates new physical effects, but also it improves the convergence property of the overall solver. Okay, so to summarize, here we have done parametric studies on the influence of the accommodation coefficient F, which is related to the thermal resistance, as previously stated. This is the thermal resistance, and here the accommodation coefficient. And we have done two kinds of studies, the kind in a ground gravity condition. And here we observe the sensitivity of our results to the accommodation coefficient. Here, the higher value of the accommodation coefficient, and here no model, so no accommodation coefficient. This gives us a range of possible values depending on the fluid which will be simulated, because the correct value of F is not really perfectly known. There's no general agreement on the correct value of F. In the good point is that in the case where in microgravity condition, if the accommodation coefficient tends to 0, we observe that it tends clearly to the case without model. So this is when the accommodation coefficient is low, the microregion effect tends to vanish. And here we have the value that we obtain with the higher value of the accommodation coefficient. Okay. So this was our previous simulation in the microgravity configuration with a microregion model, and we can have some information on the possible effect of this microregion. Now I'm going to, if I have, yes. I can speak about the microlayer formation, maybe more quickly. I come back to this slide. This arises for much higher Jacob number, so much higher wall superheat. And we undertake some simulation of microlayer by using much more refined grid than in the case of the contact line regime. And we have performed in several years ago some simulation where we can observe the formation of this very thin liquid film between the bottom of the bubble and the wall. Here you have a very thin liquid film in which strong heat transfer occurs. If we take a zoom of this microlayer, we can see this microlayer advancing, developing, and next a kind of dewetting which makes disappear the microlayer. Okay. Here we have typical simulation in the contact line regime and in the microlayer regime. So the only difference is on the wall superheat. So in the contact line regime, we just have a peak on the heat flux. And in the microlayer, you have a peak on along a kind of plateau where the heat flux is much more important. There is a huge difference on the computational resources which are required to perform this simulation. On this simulation, this one has been carried out with 4,000 points in each direction, where this one, I think, 500 points are sufficient. We check the convergence of our simulation in the microlayer, which was a kind of a challenge. With the size 0.5 microns is for the mesh 4,000 square, and this one has been carried with a mesh of 0.25 microns with a mesh of 8,000 square. And we observe that for these two very refined grid, spatial convergence on the bubble shape. And here, a snapshot of the velocity field inside the microlayer. Here we can see the strong evaporation along the interface. So finally, we can here observe some heat flux distribution along the microlayer formation and depletion. And finally, after performing many simulations, we obtain a curve which gives us a kind of transition between the contact line regime, which are the red point, and the microlayer regime, which are the green points. And this can be summarized with this correlation, which is connecting the Jacob number, the capillary number, and the contact angle with this term, which must be up to 1 divided by A power 3, with the following value of A, and which give us the frontier between the contact line regime and the microlayer regime in green. The orange points are kind of a transient point. Okay, so the question we have to answer now, if we have a contact line inside the microlayer, we can assume that a microregion exists also at this point, because it acts at much smaller scales than the microlayer. So we have performed some numerical simulations that are coupling our microregion model, DNS coupled with microregion model, in configuration where a microlayer must appear. And we undertake some comparison with the experimental data of Mattia Bucci, your brother, the black point, And here, the blue curve is the DNS without microregion, just a simple DNS without accounting for microregion, but we can say that it corresponds to a DNS with an accommodation coefficient of 0. And here, a DNS with accounting for the microregion with the following value of the accommodation coefficient, 0.005. And what we observe is in the case where we do not account for the microregion, the bubble volume is increasing much more quickly than in the case with the microregion. This is not very intuitive results because we add a flux, but our volume is decreasing. But the impact of the microregion is also to move the contact line velocity, and as the contact line velocity is higher when we account for the microregion, the microlayer length is lower. So the overall heat flux is lower. So there is a strong impact. What we observe in this preliminary simulation is that the microregion, can have a strong impact on the microlayer length, and so on the bubble growth. Okay. Finally, if we compare two experiments, I will say not too bad, but not perfect. We have still some discrepancy with the experiment, and currently we think that we have to add more models on the contact line velocity, since we do not account for the local contact line velocity in our microregion models. And I think that in the case of microlayer, where the contact line is moving much faster than in the contact line regime, we will need some additional models to account for the local contact line velocity. So this is still a work in progress on this point. Okay, finally, how many times, Stefan?
You still have 10 minutes.
10 minutes, okay. 5? Okay, so quickly. All these simulations are very demanding, computationally demanding. They ask a lot of computational points and computational resources, and it's good for the science to understand well phenomena, but for engineering application, it is hardly practicable. So we are currently interested in integrated models for large-scale computation. For example, if I take this simulation, which is similar to the previous, to the first simulation I have presented, just a bubble is a contact line regime. This is the same configuration. So we reproduce the experiment from Sun very well. But this is an axisymmetric simulation, and it requires 500,000 points. If we generalize this to one bubble in 3D, it will require 1,000 points in each direction, because if we are in 3D, we consider there's no symmetry, and it will require 1 billion points. Of course, if we just take a coarser grid of only 500 points in two directions, it will be just 100 million points, and the result will not be so bad, but it is still very expensive for just one bubble. And if we are interested in several bubbles, it becomes too costly from the point of view of a computational resource. So there are two means to overcome this issue. You can try to use adaptive grid to have more bubbles and to refine locally only at the interface. And I think there are very good code which is developed here for that kind of thing with Basilisk. But another possibility is to define integrated models that can be that can replace the fundamental equations to enable computation with coarser grids without solving fully the thermal boundary layer. If we take interest to the numerical results obtained with different grids, so the more refined is the red, we see that the green is not so far from the red, and if we use a coarser and coarser grid, we see a strong discrepancy, and we have here the sensitivity of our numerical method to the grid size. So, the DNS with a very refined grid, just a snapshot to visualize the thermal field locally. The important point is clearly to solve accurately the derivative all along the interface, on all points all along the interface. As for a well-resolved simulation, and if we have a coarse grid, we see that the temperature field is not very well reproduced with a coarse grid. If we plot the total mass flow rate with time, the temporal evolution of the total mass flow rate, we see with the DNS there's a strong peak at this moment, and next a decrease. And with the coarse grid, it is strongly underestimated. And it is the same for the curvilinear distribution of the mass flow rate at a given time. This is just the curvilinear distribution of the mass flow rate at a given time. For the fine mesh, we have a peak here and higher value here, but for the coarse grid, it is still strongly underestimated. So the idea is to model this mass flow rate as with two terms. One term which is appears in the vicinity of the contact line. This is not microregion. This is a region much thicker than the microregion. So this case does not integrate microregion or microlayer model. This is just the simple case of a contact line without microregion. There's a peak on a kind of plateau. So we can define a simple model where the mass flow rate, the boiling mass flow rate, depend on a peak, which is this one, and a kind of plateau, which will appear all along the interface. The abscissa is along the interface, the curvilinear coordinate. And finally, what we observe is the integral of the peak is not very important. Its effect is less than 10 or 5%. And the most important point is the plateau, which depends mainly on the volume of the bubble. So we can just define a correlation on this plateau and to introduce it in our solver to replace the well-resolved boiling mass flow rate and to compare our simulation with a refined grid without integrated model and a simulation with a coarse grid and an integrated model. So the coarse grid is 64 for times 128, and here we see a rather good agreement of the simulation integrating with an integrated model. This is qualitative. So just a snapshot on the velocity to see that it looks rather similar at a given time. And now we observe here the orange point, which comes from the integrated model, which is compared to the DNS, well-resolved DNS, and we reproduce roughly the same trend and a much lower mass flow rate than in the case with just a coarse grid. For the temporal evolution of the radius, we also have good results in comparison to the well-resolved DNS and to experiment if we use this integrated model with coarse grid. Okay, so this is a kind of publicity that my student makes for his method. So as the time step is 30 times bigger and the number of cells is divided by 64, the computational time is globally divided by 2000. So this is a huge progress in terms of computational times. On the other hand, the difficulty is our plateau, the value of our plateau depends on many parameters. So we need to do a simulation for each parameter of a large range of parameters to next extrapolate to define some law for integrating the variation of the Jacob, of the contact angle, of the density ratio. And here we have some curve of the simulation, the prediction of the simulation with the point on the circle, and with the cross, the prediction of the model, which give a good agreement in for all these parameters. This has required several, maybe 1, 2, 3, 4, 5, 6, 7. This requires approximately 200 simulation to have the database. 200 well-resolved simulation to next define the parametric sum fit to which integrates the effect of the different dimensionless number. Previous one was on the departure diameter. This one is on the growth time as a function, the frequency departure, and it also gives a good agreement between DNS and integrated models. And finally, a last point. This is a comparison on the temporal evolution of the mass flow rate obtained from well-resolved DNS and with integrated model. Well-resolved DNS in a continuous line and dash line for integrated models. So this gives a rather good agreement for this. So finally, to conclude, I have presented some development on the coupling between a DNS solver and a microregion model. We have investigated on the impact of the microregion on the global bubble diameter. I also presented some numerical simulation in the microlayer regime and also a coupling between a microregion at the contact line with simulation in the microlayer regime, and a last study which is under progress of an integrated model for nucleate boiling in the contact line regime. However, many open questions remain. So how to obtain reliable value of the accommodation coefficient as an input for numerical simulation? So this is a good question for experimental guys, as Matteo. How to model the contact line velocity during the deweighting? This has not been implemented in our microlayer simulation. And further work on integrated model accounting for microregion and microlayer are still required to undertake simulation at much larger scale. Thank you for your attention.
Questions?
I have a question about your boundary conditions. So, what's your boundary condition for level set?
Yeah.
What's the boundary condition for the level set?
The boundary condition for the level set is just the gradient of the level set along the normal is equal to the cosinus of the contact angle.
So it's constant.
Yes. This is constant contact angle. But in the case where we consider a microregion, this is constant, but not in time. It can vary in time with the local superheat, which is a variable. This is spatially constant, but not in time. Other questions?
I have a couple of questions. First of all, I really enjoyed it.
Thank you.
the slide where we discussed the effect of the wall conductivity on the on the contact line evaporation. I think is
This one? Yeah.
So, in my understanding, having a higher wall conductivity will be closer to the theoretical condition where the models were developed for. Because this model were developed for a constant wall temperature. So essentially, an effusivity that tends to infinity. So, in my understanding, the model should be more realistic when the when the conductivity is infinite and the effusivity is infinite. So, how do you explain the fact that without the model you have very good agreement and with the model they come apart?
There's no agreement. This is just the sensitivity to the model. If you have the model on a low thermal conductivity, you do not have effect of the microregion. On the other side, if you consider a high wall conductivity, 50 is high, the impact of the microregion is increasing.
Sure, but in the experiment, that's done on silicon, it's done on which material? In the Ruby experiment.
Yeah.
What is it? Is it a sapphire?
Sapphire, yes. And the conductivity is 25, that kind of thing. It's close to the.
It's an excellent agreement, and I totally believe that's the phenomenon. Somehow this thing kind of puzzles me.
In fact, what we observe is for low conductivity, the microregion tends to disappear because there's no temperature discontinuity at the contact line. Because maybe I propose to assume that we have a thermal equilibrium. And in the case where the thermal conductivity increases, it's more difficult to ensure the thermal equilibrium in the vicinity of the contact line, and then you observe a kind of temperature jump. In all cases, you have a temperature jump, but if the wall conductivity is low, this temperature jump is very low, and it increases with the wall thermal conductivity. Here or here.
To go further on these questions, the conductivity of the solids in your experiments is known, right?
Yeah, to about 25.
Yeah, approximately. Yeah. This is not a Ruby. This is not a Ruby. This kind of simulation for Ruby. No, I do not have the correct value, but I think it is almost 25 or that kind. Maybe. No. Well, we can easily verify.
I was not paying enough attention. Are you modeling the conjugate heat flux? Or
Yes. Yes, there is a complete resolution of the conjugate heat transfer.
Yes.
Yeah.
Thanks for the talk. I was wondering that in a work by Sato, their maxima for heat flux in the micro layer happens at the end of micro layer, but in your case it happens somewhere in the middle of the layer. Does it depend on your choice of F, the accumulation, or is it which one is more?
That's a good question. I'm not sure that I have the answer to your question. I don't remember that. If we consider here, maybe this one is better. The heat flux, which increase. This is the contact line. This is the point where the microlayer thickness is lower, and you say that in the results of the Buress, the heat flux is higher at this point at the end of the. Okay, I don't remember this curve, but I think it's a bit surprising. But if the heat flux is lower, it means that the thickness is. If the heat flux is higher, it means that the thickness is lower, the liquid thickness. Maybe we should look at the curve to discuss of this, but I do not remember to this curve.
With no more questions, first of all, I will remind you we have two seminars tomorrow. One similar topic by Matteo Bucci and another by Alfredo Soldati. And thank you again, Sébastien.
Thank you, Stéphane.
I also have the approach online from